Now, the next type of binary mixture that we'll consider is a liquid-liquid binary mixture. In a liquid-liquid binary mixture, we have two components, both of which are liquids, and the component which is in excess will be called the solvent. Now, the mixing process or the process when you dissolve one liquid into another can have either a positive change in enthalpy or a negative change in enthalpy. It could be an endothermic or an exothermic process. But for the first part of our discussion, we'll limit our discussion to scenarios where there is no change in enthalpy. That is, delta H mixing is taken as zero, and also the volume change because of the mixing process is taken as zero. Such solutions are called ideal solutions. Now, although we generally assume that volume change is zero, it may not always be so. If you mix two liquids of 10 ml each, you do not always get a final volume of 20 ml. The final volume may be slightly less than or greater than 20 ml. But in an ideal scenario, or when you get an ideal solution, you have neither evolution nor absorption of heat, and there is no change in volume upon mixing those two liquids together. Now, because we have two liquids mixed with each other, the surface fraction which each liquid get will be proportional to the mole fractions. Now, prior to mixing, as you can see here, the entire surface area of the liquid is occupied by molecules of one kind, of that liquid only. So the entire surface area is available for vaporization. But when we mix two liquids together, as in the second case, a part of the surface area is occupied by the liquid A, or the red colored molecules, red color dots or spheres actually, and the other rest of it is occupied by the molecules of the second liquid. Now the rate of vaporization of each liquid will decrease in this scenario because it now occupies only a fraction of the total surface and not the entire surface on its own. Now the partial pressure which we get due to vapors of a particular liquid is given to us by Raoult's law. Please write this. And this Raoult's law states that the partial pressure of vapors of a liquid in a solution is directly proportional to its mole fraction in the solution at constant temperature. So let's say we have the two liquids A and B with vapor pressures of PA0 and PB0, and mole fractions of xi A and xi B for the two liquids. Then Raoult's law states that partial pressure of A is directly proportional to mole fraction of A, and the partial pressure of B is directly proportional to mole fraction of B. In fact, the partial pressure of A can be written as xi A into PA0, and the partial pressure due to B can be written as xi B into PB0. The validity of this equation can be understood if you take xi A as 1. If xi A is 1 in a particular scenario, then you have only liquid A when its pressure should become equal to PA0. Vapor pressure should become equal to PA0. And as xi A decreases, the surface fraction occupied by that liquid decreases and its vapor pressure decreases proportionately. Now, if we consider the total pressure due to vapors in this solution, let's call it P0 solution, is the vapor pressure which develops over this mixture. Then that vapor pressure has two components. We can write the vapor pressure of the solution as a sum of partial pressures due to the two vapors as PA and PB. So P naught solution can be written as xi A PA naught plus xi B PB naught. Xi A PA naught is the contribution of A towards the vapor pressure, and xi B PB naught is the contribution of B towards vapor pressure. Now, since xi A plus xi B is 1 in this binary solution, we can get two different forms of this equation too. We can write xi A as 1 minus xi B to get one form, or you could write xi B as 1 minus xi A to get another form. Now, let's first eliminate xi A from the equation and write everything in terms of xi B only. So P naught solution here can be written as PA naught plus xi B into PB naught minus of PA naught. This is another form of the total pressure which you get using Raoult's law. Similarly, if I write 1 minus xi A instead of xi B, I get another form for P naught solution, which is PB naught plus xi A into PA naught minus PB naught. These equations give us the total vapor pressure of the solution as a function of either mole fraction of A or mole fraction of B. Now we'll plot these results in a graph which we've just drawn here. We have vapor pressure of the solution on the y-axis and we have mole fraction on the x-axis. Now the mole fraction of A has a limit from 0 to 1. So if I plot xi A from 0 to 1, then as xi A increases from 0 to 1, you have xi B decreasing from 1 to 0, so that the sum remains 1 always. Now we want to plot vapor pressure of the solution. Let's not just limit it to the vapor pressure of the solution, just write this as vapor pressure. So we can plot vapor pressure for the solution here. We can also plot pressures, partial pressures for individual components, that is A and B. Now PA, as we wrote just a little time ago, PA is xi A into PA naught and PB is xi B into PB naught. Now plotting these are fairly simple, but I'll still walk you through it. Now when I want to plot PA, which is xi A into PA naught, so I'm basically plotting PA on the y-axis and xi A on the x-axis. So I get an equation of y is equal to m into x. The slope is PA naught, and we get a straight line which passes through the origin. The intercept when x is equal to 1 or xi A is equal to 1 will be PA naught. So you get a straight line passing through the origin, which I'll denote like this. Take a straight line graph. Now this value has to be PA naught. When xi A becomes equal to 1, that intercept is PA naught. Now if you want to plot PB, we use this equation. PB is xi B into PB naught. So you can always write it as 1 minus xi A into PB naught. So the equation for PB turns out to be PB naught minus xi A into PB naught. Now this is of the format y is equal to C minus mx, where m is minus of C. Let's write it as C plus mx, where m is minus of PB naught. So it'll have a negative slope, but it'll be a straight line. Now that straight line will have a value of PB naught when xi A is taken as 0, and if xi A is taken as 1, then PB becomes 0. So when xi is taken as 0, we get a value. That value should correspond to PB naught. And when it becomes equal to 1, that value decreases to 1. Decreases to 0. So this is a graph for partial pressure of A, and this is the graph for partial pressure of B. Now, when you want to plot for vapor pressure of the solution, we go to equation 4. Now the equation 4 is of the format y, which you want to plot on the x-axis P naught solution, so we'll call that y. This xi A is on the x-axis. So PA naught minus PB naught turns out to be the slope, and this is the intercept. So that's again a straight line, and that straight line, we'll find out the intercepts at xi A equal to 0 and at xi A equal to 1. So it will give us a clear picture of how we should plot it. Now if you take xi A is equal to 0 in this equation, if xi A is equal to 0, then P naught solution turns out to be PB naught. Whereas when you take xi A as 1, you can see that P naught solution will turn out to be PA naught. So the graph which you get will have intercepts as PB naught and PA naught. So we get a straight line connecting these 2 points. This has to be a straight line. This gives us P naught solution in this case. And so this entire first discussion, an entire plot, consists of vapor pressure which builds here, and that P naught solution is written in terms of mole fractions of the liquid components in the solution. Now let's focus our shift our attention to the vapor composition. And in the vapors we have molecules of A, we also have molecules of B. Now their mole fraction in this vapor phase is not xi A and xi B. Xi A and xi B is the mole fraction that we have in the liquid phase. In the vapor phase, we'll not have the same composition as the liquid phase, because if you think about it, the two liquids which you have mixed do not have identical volatilities. One of them is more volatile, and if one of them is more volatile, then it will vaporize to a relatively greater extent. So the vapors which you get will be richer in the more volatile component, and the less volatile component will be left back in the liquid form. Now let's call the vapor phase mole fractions as Ya and Yb. Y and Yb refer to mole fractions that you have in the vapor phase. That is the vapors which have accumulated above the solution. Let's write this down. If Ya and Yb are mole fractions in the vapor phase, then we can use Dalton's law of partial pressures to get the relative values of get the values of Ya and Yb. Now we know from Dalton's law that mole fraction of a component is the ratio of partial pressure to total pressure. Or we can write this as Pa by P naught solution, which is the total pressure. So you get the value of Ya as xi A Pa naught divided by the total pressure is xi A Pa naught plus xi B into Pb naught. Similarly, Yb can be written as partial pressure of B divided by the total pressure, that is total vapor pressure of the solution. So Yb is xi B Pb naught divided by the total pressure, which is xi A Pa naught plus xi B Pb naught. Of course, the ratio of Ya by Yb is the ratio of their partial pressures Pa by Pb. So it is xi A Pa naught divided by xi b Pb naught. Now, as we said before, there is a relative enrichment in the vapor phase of the more volatile component. So if A is more volatile than B, or if Pa naught is greater than Pb naught, means the exact same thing, then Ya divided by xi A will be greater than 1, and Yb divided by xi B will be less than 1. This means that since A is more volatile, its vapor phase mole fraction is greater than its liquid phase mole fraction. Another equation which is fairly obvious, so just let's write it down. It's that the mole fraction of in the vapor phase Ya plus Yb, the sum of mole fraction will be equal to 1, as is the general case for any scenario where you add up mole fractions. Now we have already used equations 3 and 4 before. So we'll term these two equations as equations 5 and equation 6. This is not particularly important, so we'll not number it as anything. Now from equations 5 and 6, we can write an expression for Ya divided by Pa naught. It will be xi A by xi A Pa naught plus xi B Pb naught. So I'll write that equation here. Ya divided by Pa naught, take a look at this again. Ya by Pa naught will be xi A divided by P total. Just let's write this as P total, or P naught solution as we've written before. So Ya divided by Pa is xi A divided by P naught solution. And if you take Yb by Pb naught from the equation here, Yb divided by Pb naught, you get xi B divided by P naught solution. Add these two up, and you get xi A plus xi B divided by P naught solution. So we can write this equation as Ya by Pa naught plus Yb by Pb naught is 1 by vapor pressure of the solution. This is also an important equation which you can use in question which deal with only vapor phase mole fractions instead of liquid phase mole fractions.